Ladies and gentlemen, we are entering the realm of the metaverse. Please welcome to the stage Dr. Jaksh, Professor of Physics at the University of Oxford.
Good morning, everybody. Now, about 50 years ago, physicists started to be able to trap and investigate individual microscopically small particles. And what they found was that these particles behave exactly like quantum mechanics predict in any single experiment they've been doing. So it was possible to do some of the most outlandish and most controversial early Gedanken experiments, like real-life experiments that do Einstein's spooky interaction at a distance, or Schrödinger cat states, but not real cats. No cats were harmed in those experiments. And they demonstrated the validity of quantum mechanics over time again. And if you take one of the simplest particles that they investigated, then those particles only have got two states, much like the conventional bits that we use in computing every day billions of times. Now, a conventional bit can be one of the two states that it possesses. In contrast, these kind of quantum bits can be in a superposition of those two states that it has. So it can be a little bit more in one state or a little bit less in one state in any kind of superposition of the two states that it has. Now, this is intriguing for physicists, but for computing, it's not yet very interesting. Things become a lot more interesting if you actually start to move to a larger number of quantum bits. And if you go already to 2 quantum bits, then what starts to happen is that the states of these quantum bits do not just depend on them individually, but they can become dependent on one another. The quantum bit can be in a superposition of states that not just are their own states, but also the states of the other qubits that are around. And so 2 qubits can start to become entangled in ways that are not imaginable in our everyday world. And that means that the number of states that are available to those kind of quantum bits is much, much larger than anything we know from the classical world. And if we move and add a qubit every time we add 1 quantum bit, the amount of information, the amount of data that is stored in the state of these quantum bits doubles. So you kind of add qubit after qubit after qubit, you double the amount of storage capacity every time you just add 1 qubit. And if you move up to just 50 of those quantum bits, you would actually be able to store about 64 petabytes of data in that state of the qubits. Now, that is much more than we can usually handle in standard classical computers. But also, we can actually then manipulate those qubits in a way that we act on those 64 petabytes of data all in parallel. Why do I say 50 qubits? Well, earlier this year, scientists have actually demonstrated the first quantum devices that can actually act on 50 qubits and can be controlled in a way that's sufficiently good and sufficiently accurate to start thinking about doing quantum computations and to actually start to have that power of quantum computing where you can have huge amounts of data and process that data all in parallel. So just imagine a machine that has got trillions of computations in parallel and acts on these huge amounts of data. This doesn't come for free. So while it's, of course, very enticing to think about being able to process large amounts of data all in parallel, there are some kind of restrictions that we face in operating these computers. And one of the most important restrictions is that it is kind of hard to get classical data in and out of these quantum computers. Quantum computers are not very good at storing the data, so They're basically building memories like we're used to, flash drives and so on, is kind of challenging because these quantum states are very fragile. And also, any computation we do must be linear and reversible. So we can't throw information away like in a classical computer. All the information that's inside a quantum computer must stay there. So that requires new paradigms for computing. So when we think about how we're actually going to utilize this kind of huge storage capacity and this parallelism, we need to start thinking differently about how we want to do this compared to what we do with classical computers. And what I would like to do now is I'd like to actually explain a little bit on how we approach this question for a specific example. But pretty much that same approach can be used for other kind of examples as well. And in particular, what we would like to look at is we'd like to look at computational fluid dynamics problems. So computational fluid dynamics problems arise basically in everything that moves. If you want to build an aeroplane, a submarine, an inkjet printer, or want to study the flow of blood in our bodies or do combustion engines, chances are there is a fluid dynamics problem in there somewhere. And fluid dynamics problems are challenging to solve because you can have flows that become turbulent quite easily, and turbulent flows, in order to describe them, you need to cover a large range of length and time scales. So you need a lot of data to be able to store and process those kind of flows and their behavior. And that's exactly what we can do with our quantum computers. But importantly, that flow still has some structure. We know from the underlying physical model that it can be, in principle, worked out from very simple to write down equations that just take up a couple of lines. And so there is some structure in that flow, and so that means we can hope to be able to actually write those flows into these quantum bits without facing the challenges that we usually have, that this is very slow and not a very simple process. And so we went on and actually started looking at whether that was indeed possible. And what you see up there is a diagram that basically summarizes our main findings in this area. So on the x-axis, you move along the quantum bits in our quantum register, and on the y-axis, the amount of entanglement is shown that we need between the different qubits in this quantum register. The dome that you see is the maximum amount of entanglement that is available in the quantum system. The white area is what is not needed. The red area is what is needed to represent the fluid flow. And so what you see here is that the vast amount of entanglement that is available is actually not needed. This is a logarithmic scale, so only a couple of % are shaded in red there, and it is thus possible to write these types of fluid flows into quantum states relatively easily, and we know how to do this. And so that basically overcomes this kind of question of how do you actually read and write, or write in particular, information into quantum registers for this particular example. But this doesn't solve all the problems yet, because we still have the limitation of actually needing to do linear operations only, and we are not very good at storing information in quantum computers, which is good at processing them. And so what we've come up with is a scheme that actually separates the different tasks between classical standard HPC computers and quantum computers. And we basically share the burden of doing any computation between these classical and quantum computers and ask each part to do what it does best. So the quantum machine will take care of analyzing the flow, representing it, processing it, while the classical computer on the other side will actually do the task that the quantum computer is not good at: store things, optimize them, interact with the user, and basically do all the things that quantum computers are not yet very good at. And in this way, what we achieve is that we can minimize the amount of information flow between the quantum computer and the classical one, so we overcome this question of how do you actually read in and read out quantum information for practical applications. And we also can overcome a large number of other issues that arise from the requirement to do linear operations on quantum computers only. Now, with this we basically are on the path towards creating very flexible frameworks for doing what we call quantum industrial design. So you basically have a certain product that you want to optimize its shape for. There is a fluid flow that affects the physical behavior, the physics of that object as, say, the car moves or the airplane flies. And there are a number of restrictions that arise from production processes and other kinds of constraints that don't arise from the physics of fluid flows. So what we can do in this case is basically we take our hybrid approach, we ask the classical computer to take care of the constraints to actually allow the engineers to do their work, and in the back end, the quantum computer actually works out what are the effects of the flows around this object, how do we optimize the shapes, and actually processes that kind of large physics problem of solving turbulent flows in the back end. And hopefully, of course, the idea would be that this is completely hidden from the user so that people who want to run these kind of applications do not have to really learn how to do quantum computer programming. Well, thank you very much for your attention. That's all I wanted to say. Thank you.